Hi there, folks. Today we're looking at direct variation. And direct variation is just a special version of a linear equation that's in the form y equals kx. All right. And here's the thing, y equals kx. You could also think of it this way. It's just y equals mx plus b, except it just so happens that b is a 0, all right? This is no different than when we do y equals mx plus b, except that the y-intercept is going to be a 0, so it goes through the origin. So if we have a line that goes through the origin and has some kind of slope, then guess what? It's direct variation. It's not any different in terms of the patterns. It's not any different in terms of the way we graph it. All right, the only difference is that we call it something else. And yeah, instead of m, we now have listed k. All right. Is k the same thing as m when we go to graph it? Yes. Does it follow the same patterns as m when we're looking at the line? Yes. Do we call it m? No, we call it k, and it's known as the constant of variation. All right. It's basically the thing we're multiplying by in our equation. But that was the same thing as m, all right? So again, think of it like y equals mx plus b. So if we have a line that goes through the origin, it's direct variation, all right? Instead of calling it m, we call it k. Instead of saying slope, we say constant of variation, all right? For example, if we look at the equations themselves, all right, let's solve these for y. Let's get y by itself and see if it looks like y equals kx or if it looks like y equals mx plus b. All right, for example, if I look at this guy, to solve for y here, I just divide each side by 3. And so when I do this, it's y equals, that is a 7/3 x. And so now I ask myself, is this the equation of a line? And does this line go through the origin? The answer is yes. So this is direct variation. So yes, this one is direct variation. Okay? If I look at the next one, again, I want to solve for y just like I normally do when I'm putting this like in slope-intercept form. So I'm going to divide each side by 7. And here, this is my distributive property. 14 divided by 7 is a 2. 7 divided by 7 is a 1. And there it is, y equals mx plus b. But ask yourself, is this a line? Yes. Does it go through the origin? No. It has a y-intercept of 1. So yeah, this is a line, but it's not direct variation. It's not the special case of the line that goes through the origin. So this is going to be a no. Okay? Again, it's the same thing. If I looked at something like these guys, all right, let's determine if this is direct variation or not. And remember, we can tell if this is a linear equation by looking at the pattern between the y values and the x values to see if it's the same each time, all right? And remember, we're looking for a constant increase here. So like this one, here it goes up by 2, then it goes up by 1, then it goes up by 3, all right? And again, it's not that this is constant. Yeah, 2, 1, 3, that's okay. But we want to see if it's constant in terms of the change in y over the change in x. We're kind of looking for slope here. And so this one, it goes up by 4, then it goes up by 2, then it goes up by 6. But now the question is, if I did 4 over 2, right here, 4 over 2, that gives me a 2, which is kind of like our change in y over change in x. Here, 2 over 1 is also a 2. Here, 6 over 3 is also a 2. And so the question is there a constant rate of change? The answer is yes. And the constant rate of change, the fact that that is 2 every time, makes this thing a linear equation. All right? So now that I know this thing is a line, I just have to ask myself, does it go through the origin? And for that, I kind of need to extend the xy chart in one of these directions. So maybe up here, I would say, hey, let's put a 0 here. And continue the pattern. Like if I went down 1 here, I would have to go down 2 over here to keep that constant rate of change, which would also be a 0. So we already know it's a line because of the constant rate of change. Now we can see that this thing goes through 0, 0, which means, yes, this one is direct variation. Okay? And if you had trouble identifying that 0, 0, fill in the gaps here. Like here, if I stuck a 2 in between here, I'd have a 4 over here, right? If I stuck a 5 and a 6 in between here, you could see that I would have a 10 and a 12. And so now that pattern becomes a little bit clearer. Here going up by 1s, over here going up by 2s. So keep the pattern going the other direction. Go down by 1, go down by 2, and see where it lands you. All right? If I look at the next one, I see that it goes through 0, 0, so that's a good start. but I need to determine if this thing is a line. I'm looking for a constant rate of change. So I look at this and say, okay, it goes up 1. So it's going up by 1 each time over here. Over here, it goes up by 1, then 2, then 4. And so if I compare these right here, 1 divided by 1 is a 1. Here, 2 divided by 1 is a 2. 4 divided by 1 is a 4. So the rate of change is 1, 2, 4. It's not a constant rate of change, which means this is not a linear equation. So the question is it direct variation? Well, direct variation is a line that goes through the origin. So the question is this one a line? No. Does it go through the origin? Yes, but it's not a line, so it's not direct variation this time. It's got to be a line that goes through 0, 0. Okay? If I look at the next one, again, look for that constant rate of change. Here it goes up 1 each time. Here up 3, then up 3 again, then up 3 again. And again, it's not that those values are the same. We saw that in the first one. It's that the rate of change is the same. So here, 3 over 1 is a 3. Here, 3 over 1 is a 3. Here, 3 over 1 is a 3. This has a constant rate of change in y over change in x. If the rate of change is constant, then this thing is a linear equation, all right? This is how we determine if something is a linear equation. We look for a constant rate of change, okay? Essentially, we're looking for slope. And so since slope exists, since it's a constant rate of change, this one is linear. I just need to fill in the gaps a little bit. Let's see. If I go down 1 over here I would go down 3, so that would be a 1. I'm just extending the table. I'm extending the chart in one direction. So now I know it's linear, but it doesn't go through the origin, so this one is not direct variation. Okay? And then the last piece of this thing, these are kind of a classic type example that we'll get with direct variation. It says y, suppose y varies directly with x. That's the problem's way of saying, hey, this is direct variation, all right? This is going to be of the form y equals kx. And there are two ways that you can approach this, okay? The first option is to actually write the equation. And to write the equation, all we need is the k value. So, for example, I know this one is direct variation, so I know it's going to be y equals kx. And then it tells me that y is a 9 when x is a negative 15. Well, I can plug those values in. Y is a 9 when x is a negative 15. And see, I can solve for k now. So I could solve this for k and figure out what my equation is supposed to look like. And so when I do that, I get k equals, this is going to be a negative 3/5, which means the equation of this line is y equals negative 3/5 x. And that's it. That's direct variation. And so to answer the actual question, it says, what is y when x equals 21? So all I have to do is plug a 21 in here. So I plug a 21 in, and it's just a little bit of multiplication. So that's y equals a negative 63 over 5. And that's it, okay? The other option here, because it's direct variation, and this only works with direct variation, it doesn't work with any other linear equations, because there's only one thing I'm multiplying by, it makes the values proportional. In other words, when it says direct variation, y is a 9 and x is a negative 15, I could say, hey, the ratio of x to y, or y to x, it's 9 over negative 15. See, that's y over x equals y over, well, the x value that it gave me is 21. And now I can solve this thing for y, okay? And I can solve by cross-multiplying. Ready? Negative 15y equals, and yeah, the value here is a little bit bigger than it was in the other one, but looks like a 189. And now I divide by a negative 15. And spoiler alert, each of these is divisible by 3. So if I divide the 189 by 3, I get a 63. And if I divide the 15 by 3, I get a 5. So you notice I get the same answer either way. It's one of these special things that happens. Direct variation kind of allows us to have proportionality between x and y. So we can either write the equation using the k value, or we can use proportions to solve for the missing variable, okay? Just make sure that here I did y over x, so over here my second had to be y over x. If you had done negative 15 over 9, that's x over y, then you better do 21 over y. You better do x over y over here. So make sure you set up the proportion correctly if you do it that way. The only advantage to this first option is that we'll run into situations like that a little bit later where maybe we'll be plugging things in to solve for different pieces of an equation, okay? And it's good practice for that, all right? But direct variation, it's just a special case of the line. It's a linear equation that goes through 0, 0. You can tell that things are linear if they have a constant rate of change, all right? And then to determine if it's direct variation, you look for it going through the origin, okay?